Okay. Anyway. Okay. Can you see now my slide deck?
Yes, yes.
Okay. So let's move on. Okay. So I'm gonna be talking about I'm gonna talking about the a bit of something that I mentioned, which is the uh, why financial markets, right? So financial markets, right? Some sort of have many elements that make that make reinforcement learning like a suitable approach. Like they're dynamic, they're probably non-stationary. Non-stationary. This is a big this is a big open question. Obviously, to what extent we find, well, I do think that that markets are weakly non-stationary in the sense that sometimes are really non-stationary. Sometimes you have new factors that emerge that make changes in the distribution of the markets that are hard to predict and foresee. Like, for example, let's imagine the current state of the market with the tariffs, in which you have policy impacts in the market that far from being, so to speak, are far from being something really predictable. But then, in the sense of the policy impact model that you have to build is not an easy one. But then you also need to figure out how these how these tariffs are going to be applied, when, where, how much, and so on and so forth. This is a hard problem, right? There are and there also are in a context in which we need multi-agent environments, like, for example, in high frequency trading, or in execution, right? We're obviously or we might be, right, actually in a multi-agent setting. And to the best of my knowledge, we haven't seen a lot of work on multi-agent environments, right? So in addition to that, classical quantitative techniques can be struggling with adaptability or risk, or even risk management. But this is so RL provides another paradigm in which we can use our models. Again, it's not the only one. Uh, uh, okay, so I'll be talking about quickly about MPTs, MDPs, and MGs, right? Obviously, not going to be spending a lot of time talking about MDPs because everybody knows, and I'm going to go talking a bit more about Markov games, because the multi-agent setting, again, to the best of my knowledge, it's been much less explored, and it's some sort of a way to another way to investigate the market. Then, in terms of policy gradient methods, right, I would say that the latest innovations coming from LLMs, large language models, right, provide us new ways to some sort of do policy gradient methods. Like, so obviously we all know proximal policy optimization, and now we can add to this GRPO, group relative policy optimization, which has almost, let's say, 6 months, and it's coming from the DeepSeek team in China, who's done a terrific job innovating in ways in which these algorithms can be better learned, and can deliver some sort of more robust implementations, right? Obviously, LMMs provide a similar use case, right? Why is a similar use case? Because in the fact that we need to be predicting the next token is a similar thing that we need to predict next action. So it's a sequence of things. I have a state space, so it's more, and I have to choose among a highly dimensional action space, which is 50,000 words or even 150,000 words at each and every step, right? One can say transformers and autoregressive transformers. Are some sort of a form of reinforcement learning. And again, there's been there are a lot of connections, and reinforcement learning is also proving to be crucial for the development of more robust LMMs and so on and so forth. And here I want to make the again the parallel between alpha star, right? And alpha star it was kind of this, right? But the alpha star was already thinking, so to speak. That might seem a little bit provocative, but I think that alpha star was already some sort of a reinforcement learning method that at the same time was sort of one of the first models that was kind of intelligence, because itself was able to generate, again, right, to generate solutions and try to evaluate these solutions and implement these solutions and keep going and so on. Okay, another interesting or a very important thing for finance is this idea of distributional RL, right? Which is, instead of using a point prediction point, like for example the one expected return, the idea is, can I produce the distribution, the probability distribution of the rewards, right? If I know well the probability distribution of the rewards, that will allow me to do much better choices, obviously, than just the expectation, right? And so on. But I think that distribution RL or let's say fat tail risk measures and so on always have the same aspect. The thing is that the moment you want to know more about something you don't know much about, right? For example, again, you want to know the distribution of the returns, right? That of a specific portfolio that you've chosen, right? The moment you explore, for example, the tails of these distributions, it's the moment in which the estimation risk is even larger, right? Okay, estimation risk is, have I figured out correctly the probability distribution of this? Is this and even if I figure out the distribution of these, do stationarity allow me to some sort of still use that distribution that I've estimated from, for example, historical? That's it, something that might lead to the idea that I could build first, before using RL, I could build first generative models. So the joint probability distribution of the returns, for example, using Gaussian processes, or for example, using normalizing flows, or diffusion models, or even vector variational autoencoders and things like that. So again, there's an incredible richness of different settings, and that's what makes RL and finance so complicated, and at the same time so promising, because if I'm able to build a framework that explores better some features that might be important for the model, instead of, for example, building, one might say, I can build here a supervised learning method. There's nothing tremendously different from building an LSTM model that forecasts returns than building an RL model that has LSTMs or has transformers to make these predictions and so on. So very long introduction, sorry. So I'm not spending a lot of time with MDPs. Everybody knows what's an MDP. It's state space, action space, transition dynamics, reward function, discount factors. This reminds me, obviously, courses like David Silver, that I'm sure, everybody in the audience is familiar with them, right? But obviously David Silver, and obviously Richard Sutton and Barto have done a terrific job, obviously formalizing what's reinforcement learning and so on, and obviously, some other people, right? That you'll find this in the paper. Okay, so let's move on. So we all know about the Bellman equations, right? Provide the ways to update the value of a state or state action pairs based on expected rewards on the values of subsequent states, right? And the standard assumptions, iterative methods like value iteration or TD, temporal differences converge to a unit fixed point and guarantee a solution to the optimization problem. Right here, there's lots of different directions in which I could some sort of modify these, and obviously one of them is like, I'm not only interested in optimizing the expectation of these rewards, but that I'm interested in optimizing, in addition to that, for example, the C bar, and so on and so forth. Right now, what happens with the multi-agent formulation? Then this is called the Markov games, right? And are collections of interacting agents, and you can build the Markov games framework that has a finite set of agents that, for example, institutional traders and market makers, each with their own objectives or strategies. One might say that this is kind of an agent-based model, right? Agents-based model was some sort of what we were building, and everybody is still obviously building, is like, how can I some sort of build a generative market, an artificial market model, a model that some sort of a complex system that models a different set of agents, each of them with different utility functions or objectives or strategies or reward functions or policies or whatever you call it, right? And you want to build that in such a way that creates some sort of markets of or at least artificial or synthetic financial markets that kind of make sense, right? So that's a lots of caveats here, and there's a lot of richness in that formulation, in the sense that then we need to start discussing Nash equilibriums and things like that, right? Nash equilibrium is an agent can improve an outcome by to deviating, right? Or there's the existence is proven for some stochastic games under suitable conditions, but right, in general, what we have is high dimensionality and complete information and stationarity of agent strategies, right? So even when we play poker game with more than two players, if I remember correctly, there's no Nash equilibrium, right? So there's no, and in the sense that no player has guaranteed, I wowould say, the victory, because there's too many interactions and superposition and things like that make the game uncertain, the outcome of the game uncertain, right? When you add stochasticity, when you add highly dimensional spaces, when you add highly combinatorial, like for example chess is some sort of one of these games in which you cannot but you can almost brute force, right? Okay, I was discussing yesterday with somebody saying, right, why RL is meant to beat humans, or these algorithms. It's easy, right? RL will, with a huge amount of compute, will be able to brute force the action space, the value functions. You will be able to evaluate many more, some sort of steps ahead. For example, if you're playing chess and so on, right? So one common way to model multi-agent systems is the centralized training with decentralized execution. So trains using global information, then agents execute based on local observation. And examples are something we're working on, which is MADDPG and MAPPO, that I'm going to be talking about a little bit later on. Obviously, right, value-based methods is something that some sort of everybody's familiar with. So Q-learning, it's one of the fundamental methods that learns the action value function directly, updating the Q values based on these observed rewards and the maximum expected future rewards, right? And DQN is the same thing, is extend Q-learning, but using neural networks to approximate these Q functions, right, for high-dimensional spaces. So I would highlight here that the innovation for stability. So one of the problems of building these high dimensional models is obviously convergence and stability. So you have to tweak a big time these models using experienced library buffers, target networks, and double Q learning to reduce overestimation. Right? These techniques can help stabilize training and improve convergence. Now, the policy gradient methods, right, is methods that directly optimize policy parameters. So these methods adjust the policy based on the gradient of expected reward with respect to policy parameters. Advantage gradient policy gradients reduce the variance by using the advantage function, right, which measures the difference between expected rewards and a baseline value, right? And here, one of the crucial things that's proving to be really useful is actor critic environments in which you need a policy network characterized by theta and value function estimators, also parameterized. And then generalized advanced estimation can improve the stability of these by balancing bias and variance trade-off. Now, one way to some sort of so I think with Schulman, Schulman was the inventor, so to speak, of proximal policy optimization. Is and it's a major advance because if limits policy updates to avoid disruptive changes using important sampling ratio to measure the difference between new and old policies, right? So again, it's one way to stabilize, and here, right, finance-wise, it can stabilize learning volatile market conditions, sample efficient, conditional to compared to other traditional methods, and is compatible with something really important, which is something I have mentioned, which is that you can use these methods to some sort of produce a prediction, right? But you can also use some of these methods to continuous action spaces. For example, the portfolio allocation problem. And I tell you, it's not easy to some sort of build neural networks that actually, instead of just giving only the return, the expected return, produce for you the allocation directly, right? We wrote a paper, I think, almost 8 years ago with Sonam Srivastava talking about this, and there are many, right? And even Matthew Dixon in his book of machine learning for finance theory and practice, Matthew Dixon kind of proves that if you're in a setting, if you're in a let's say, I would say reasonably Gaussian, multivariate Gaussian model, right, and you're trying to optimize the allocation, right, you're actually, and you use as a reward some sort of the Sharpe ratio and things like that. Obviously, what it emerges from doing reinforcement learning is something not very surprising, which is the modern portfolio theory, invented by Harry Markowitz in 1952. Now, let's say, our brothers of, so to speak, of the two LMMs, right? So we are also. I am also personally very interested in LMMs. I think they're incredibly useful, and one way in which I would say Chinese researchers from DeepSeek, right, some sort of figured out that actually one way to make PPO even better, right, was using this GRPO, Group Relative Policy Optimization, and it's about doing this kind of normalization, right? This kind of a normalization that normalizes advantages across batches, as we see here in the equation, right? Some sort of Z-scoring them, so to speak, right? In the sense that you only want to consider, right, some sort of so it normalizes advantages across batches. It draws to reward scale variations and improves training stability. It's kind of a Z-score if you see here in the equation 11. It's kind of a Z-score. Now, the latest, one of the latest let's say, innovations here is this idea of GRPO, DIPO, decoupled asymmetric policy optimization, which is, I think, 3 months old, right? I wrote a paper, and it's about, again, asymmetric clipping, token loss aggregation, and dynamic sampling of effective batches. I think this is a wonderful paper, another wonderful innovation, right? So these technologies, GRPO, DPO, enable more nuanced optimization, or might enable more nuanced optimization for financial returns, addressing some unique challenges. So we haven't tested. So we have. So instead of doing PPO, it's very easy to implement GRPO and DAPO. Right? I really, and we're doing that. Right? I think that again, these are clever tweaks to the policy optimization algorithms that really benefit, right, when you have large dimensional spaces and so on. Okay, this full idea of DRL, which is not deep reinforcement learning. You see that I'm not being very specific about deep RL, right? I assume everybody in the audience know that obviously many of these things, you'll have high dimensional action spaces and in action pairs and so on. And there, obviously, you need to be using deep learning, right? But and I'm not being explicit about this. I think that I will write about this in the paper. I think transformers can also be used in reinforcement learning, obviously, right? Transformers are some sort of glorified LSTM, right? And here we're talking about, obviously a sequence of actions. So a policy is a sequence of actions, and we're navigating a game. And it's a sequence of situations, so to speak. It's when you play Go, it's a sequence of plays that we do, and obviously the sequence matters, right? The sequence matters in the sense that it's important to understand what Lee Sedol did in the first move, or what Lee Sedol did in the fifth move, and so on. Anyway, so here distribution RL is the ambitious idea that, okay, instead of 1 point estimate, we want to capture the full distribution of possible returns. This would facilitate still risk management, risk-adjusted decision-making, uncertainty quantification, robust policy learning, right? And obviously, for financial markets, one might say, right, at the heart of modern portfolio theory, there's a flaw, so to speak. There's a caveat. It's if the distributions are not symmetrical, elliptical, then what might happen is that mean variance is actually not the optimal, right? When if you, let's say, you should start considering fat tail returns. One thing that I did in a previous paper was, okay, there's nothing in when you try to optimize mean variance, there's nothing that you can also add other moments of the distribution. So you could add mean variance, and in addition to the variance, put kind of a CBA constraint. You can also put their diversification constraints or diversification. In the audience, we have also Alejandro, who's done a terrific job in kind of also addressing other very important aspects that also can some sort of be added here, which is the whole thing of trying to add causality, right? Causality is also something that it might be important and so on. It's not an easy thing to model, right? As we all know, in high dimensional spaces, finding the common causes and all the kind of stuff is kind of a not trivial thing, right? Obviously, in finance, we have lots of non-trivial aspects in modeling, right? And this is one of the things that needs to be fully captured in your RL model, in the sense that your RL model should be some sort of be able to tackle with asynchronicity, should be able to tackle with non-stationarity, with sparsity, with sparse rewards and other kind of stuff. Everybody that has worked in these pros know how hard this is, right? So there's clearly not. And here, just to finalize this slide, you know, I always say the same thing that I did at the beginning. You should never underestimate the difficult thing that represents. And the more things we want to be our model to speed, like for example a full probability distribution, the harder it will be if we have, for example, sparse data. Right? Again, in one way, in one. So sometimes we just want to do a bond estimate, which is an expectation of a return, and the other we want a full PDF, right, and so on. Or maybe we can do a full characteristic function, and so on. It might be anyway. So let's move on. So there are different ways to some sort of be looking at the distributional RL methods. Some sort traditionally, we have this categorical distribution RL C51, right, which approximates return the fixed set of atoms. Have these network output probabilities. Then the Bellman update projects target distribution of the fixed atoms, and it enables a rich distributional modeling. It captures multimodal return distributions. Then there's the quantile regression, DRL, right, that represents distribution using quantile functions and so on, and it can provide direct estimates of BAR, CBR, right, barrier risk or expectation shortfall. And it's robust to outliers in return distribution. Well, I wouldn't be so optimist like using the word robustness and outliers. Okay, I think this is a difficult marriage, right? A difficult marriage of having robustness in outlier estimation is per se, or it might be per se a contradiction, because outliers you're going to see only a few of them. How in the world you can you see what I mean, right? So they're here non-trivial trade-offs. Again, when you want to investigate the outlierness of a distribution, it's also true that I always say the most interesting data points when you do RL or when you do finance are the outliers, is the most informative data points in your distribution. They're telling you, situations in which the probability distribution, it's either different or again, it's either very Cauchy or on so on and so forth. Okay. Now, another thing that I think it was introduced by Pacheco in his PhD, in his master thesis a couple of years ago was DSAC, right? This actor critic, distributional soft actor critic for portfolio management, which combines distributional perspective with maximum entropy RL, right? And it does the action value distribution approximated by country values, and then uses LSTMs, right? And here, right, you can do quite a lot of things with risk measures, valued risk. I'm not super with valued risk, but certainly, right, one might something I haven't mentioned is entropic portfolio management measures. I'm not that developed by Danny Cajas, right? Danny Cajas has done a terrific job on portfolio allocation and portfolio distribution, but and he's developed some entropy measures for. I'm still not fully convinced that these ones are very useful, right? To be completely honest, right? I admire his job big time, but anyway, so this seems like a good idea, right? So we can also use soft actor critic for portfolio management in order to be more distributional, right? Again, right, it's a matter of modeling choice to what extent you're going to be you're going to go distributional, or you're going to go point estimate, right? Think about if you extend the reward functions, right? For example, in the DQ and loss functions, instead of just working on this expectation, and instead of asking yourself to learn the full probability distribution, you can also be thinking about, maybe learning the third and the fourth moment, like learning the kurtosis of the distribution, and the kurtosis being penalizing some sort of your reward function, and so on, right? Yeah. Okay, reward shaping and signal enhancement. So I think I'm not, in the interest of time, because I'm gonna some sort of lead that to you reading the presentation, right? But obviously there's a lot of, again, richness, right? There's a lot of richness on how do I deal with this difficult low signal to noise ratio, non-stationarity and regime shifts, and delayed feedback from trading actions. So we know that stylized facts make markets are very efficient, so to speak. Markets are high entropy things, and so on. Okay. So now the idea of the idea of extending, right, some sort of the reward maximization, right, is like you can embed the risk constraint directly, right, a bit what you would do if you do mean variance, or mean C-bar, right, or again my approach in which you can obviously be paying to the variance, right, but you can also be paying attention to the tails, like saying I'm going to be paying attention to the tails, but with a parameter that controls that, because if I'm only doing a mean C-bar, one might say, right, that the caveats of using mean C-bar is that you're paying too much attention to the black swan event, so to speak, and you're not paying attention to the let's say to the variance, which is the normal deviation or the expected deviation between the mean of the distribution and the different observations and all that kind of stuff. Or you can use that using Lagrangian methods, right? Now, okay, so these are, again, I don't have time to go in all detail, but if somebody wants to write papers about this with us, it's like this centralized training with decentralized execution, two very interesting algorithms that need to be explored, and we are doing it, and they are reasonably easy to implement, is multi-agent deep deterministic policy gradient MA DDPG and MAPO multi-agent proximal policy optimization. Both extend, but obviously you have MAPO extends the PPO to multi-agent settings, right? And there, right, you also might think about the multi-agent GRPO, multi-agent DAO, and all this kind of stuff to see if you also need to some sort of innovate because of the convergence of these models is kind of tough, right? And so on. This is very important because everybody's talking about agents, and at the same time, nobody's talking about the ultimate here that is needed when you're using agents, which is you need to actually optimize, right, the agents' policies, different policies. So what to do when agents, what is the cause of actions when you have agents and you have ultimate goal of putting together a portfolio, right? How are they going to be combined? What is the optimal way to combine them, and so on? So this is not by any means as simple as, oh, I can write a few lines of code using the agents frameworks for the LMMs, and this is going to be taking care of itself, so to speak. This is much more. So you need to be this. You need to be somehow consider things about cooperation and competition in trading, right? So competitive market dynamics, cooperative elements, right? And then you have things like value decomposition networks, game theoretic scenarios. So it's incredibly rich, the amount of again combinations and I think RL or multi-agent RL will be at the heart of the implementation of some sort of these models, right? Agents might compete for limited resources and alpha. Nash equilibrium solution as a concept, market efficiency should emerge, for example, from competition from different players. Try to find some sort of alpha factors and so on. Alpha decay strategies become crowded, and here you have some game theoretical scenarios like predatory trading, order anticipation, strategic bid ask placement, right? So you can some sort of put your VAR model in different market situation. You can use Abite from JP Morgan in order to do that, and so on. I mean, just okay. So how you need to select model, right? So how you need to select among these some sort of PPO, DPO, GRPO, or Q learning, actor critic, and so on, right? One. So we've stated here some sort of so if market is complex, right? You should be, so this dimensionality of state action spaces. So if you work in continuous settings, you're going to need to use DRL. Risk sensitivity, obviously, then you either again you have the tough route, which is the distribution RL, or the one that I stated before, which is you can still add in the reward function some sort of additional factor, additional, let's say, elements in which you add the variance of the reward and the conditional value at risk of the reward, and so on and so forth. So also, uncertainty quantification, right? Sample efficiency. Obviously, we're talking about if somebody in the audience will some sort of say, "Oh my God," but you're understating the problem of sample efficiency in the sense that you have lots of neural networks, two neural networks, actor and a critic, and so on, and you just want to use that with in a small sample set, and that's absolutely true, right? When we do high frequency trading, we have lots of data. When we do one-day trading, we have much less data points, right? And obviously, neural networks, right, will not operate well under very low data regimes. Explainability, and again, that will obviously drive us to use smaller models when we have less data, and so on, also because of explainability and so on, right? So, so in order to answer these, if risk assessment critical, then you should consider DRL, distribution RL. Is the action space continuous? You should consider policy gradient methods. Is the sample efficiency crucial? Then you should consider policy algorithms, right? Is explainability required? Right, then you should consider simple model architectures. And if it's multiple agents, you have to consider centralized training with decentralized execution frameworks, right? Okay, so if you want to do, for example, milliseconds to seconds, then right. Oh, here it's anyway. So if you want to do milliseconds to seconds, like you have to use these policy methods. If you want to do distribution RL, you can do soft after critic, right? You have to do QR, DQN, even double, and so on. So I think in the paper this is going to be clearly stated, right? Okay, and also the state representation, right, for these high frequency methods is going to be the other book features like all the book imbalance, recent price trajectories, trade flow indicators, and so on. This might be right. High frequency is a space in which you probably want to first, given that, so you'll have a very rich data set in the sense that you have millions of data points, right? But even there, it might be a good idea to build first a gen model, right? A generative model, right? And then uh, train your RL model in simulation generated by the generative model, right? Using BAEs, bidirectional autoencoders, or even autoencoders, or even Gaussian processes. So there's a few, right? Okay, so yeah. In terms of market making, right? You can use, for example, twin delay DTPGs, right? You can use recurrent policy gradients, meta-RL for adaptation. I think. Okay, and key considerations of a market making model is you have to deal with inventory, right? So you just want to have all stock sold at the end of every session. So it's a crucial aspect to managing the inventory, right? So you need probably asymmetric reward functions, and you need to be considering something that it's in the literature. It's the other toxicity. Okay, when you do algorithmic execution, which is one of the other big problems, right? Is you want to minimize market impact, right? You want to minimize market impact, and you might say, I'm going to use Algren and Chris models from Robert Algren, and okay, so and it's about trying. You want to minimize the difference between the price you were kind of willing to execute a trade versus, right, the real price in which you're executing, right? And your job is to find a policy, right? A policy that minimizes this distance, right? And time is very important here, because the more time, as time goes by, the price probably drifts away from the original price, right? So it's a battle between market impact and time and so on, right? So you can use here again, right, twin delay DDPGs, meta-RL for adaptation, contextual bandits, and so on. There's a few again contending, right? Before concluding, I wanted to also discuss one continuous time model that I find interesting. It's not easy, some sort of to actually, I know, be using, right? This, but so this DOCTRL, right, from Igor Halperin, is distribution offline continuous time reinforcement learning, right, which with also uses pins, physics informed neural networks, right? It's the fact that we want to do continuous natural embedding of continuity, better handling of exploration errors, and sophisticated risk management through distribution. So it's also, right, again, kind of the full, right, and the mathematical formulation is this very nice soft distribution Hamilton-Jacobi-Bellman equation, right, that you're going to solve using neural networks with physics informed neural networks. Okay, so I think this is a nice model to be looking at, right? And it seems to scale well, right? It's well suited for asset allocation with real constraints, option hedging. So it's kind of a flexible approach. I'm not saying that I haven't seen anybody using it, but because it's a very ambitious model, but it can be. Okay. Now back testing and fidelity, so to speak. So the simulation fidelity is about can you build a faithful, realistic, generative model, right? of the market, of the evolution of the order book of Apple or Google or Amazon, right? So again, here we use the word high fidelity simulators. We could have chosen the word generative, or the book model, and so on. So a model, some sort of able to model the joint probabilities distribution of these issues. Then you need to be creating a model that incorporates all the book dynamics, latency, transaction cost, realistic market impact, and regime shifts, right? So this is what the model is. We have a lot of data to do that, right? And now we have very flexible algorithms. So I would say that here we're in a better position that people was trying to do, the simulators 5, 10 years ago. 10 years ago, it was kind of, very difficult, right? But we now have a lot of compute and backtesting challenges, right? So there's a lot of obviously discussion. Marcos Lopez de Prado and others have written papers about backtesting and all that kind of stuff. So I'm obviously a big fan of backtesting in the sense that you should be looking at what happened in historically. If you're using this portfolio, if you're using this strategy, if you're using this policy or another policy, and so on, right? Um, Certainly, there's a lot of caveats, right? Even if you're very strict with the back testing, even if you kind of, again, very strict and constrained using, it's only the history, right? So no back testing is completed unless you kind of able to generate a good generative model, and you're able to explore, right? Well, what is the market response of your portfolio in some sort of yes, scenarios in which we have never seen in the past, but which might be plausible considering a well estimated um, generative model of these issues. Obviously, again, a big shout to the Sphinarel GitHub and the tremendous job that Finarel team is doing in some sort of open sourcing deep RL to finance or RL to finance, designing modular designs for data processing, model training, and backtesting, supporting different market environments and training strategies, and it facilitates reproducible research and practical application. So again, a big thank you to the Finarel. Okay, there's a lot of things that right, and I think my presentation, it's kind of, I have been able to speak for an hour, and I have used the word LMM just a few times, right? But okay, so and I'm going to be some sort of also making some remarks, but robustness and stress testing, and again, this is also something that I mentioned, and this is also in my heart. What I'm saying is, while distribution RL is hard, you actually need it. You actually need some sort of be able to. So somehow robustness is about, have you been doing a good job exploring, let's say, the PDF of the let's say the ex post probability distribution function of a portfolio? Have you some sort of investigated adversarial market situations, regime switching environments, and so on and so forth? And then this idea of interpretable models, right, that some sort of at every step of the way, right, you probably should be some sort of building ways in which you explain why the model some sort of doing something, especially if the model is kind of doing some sort of counterintuitive strategies, and so on. Or imagine that your high frequency model.
À titre d'information, Reda, juste t'interrompre, hier, je pense, ou ce matin ou avant-hier, ils ont acté sur le MCP.
Yeah. Okay. Are you talking to me? Sorry.
No, he was talking to someone else apparently.
Well. Okay. Sorry.
But he didn't.
Okay. So just to finish, right? There's a lot of, there's a lot of caveats on using financial data. Again, I can't stress enough. The fact that we wrote a paper with Harry Mandel from the Federal Reserve stating that LMMs also need to operate in financial data sets that are really curated. When I say curated, I'm not saying curated from outliers and so on, but the idea of having very accurate timestamp synchronized with a global clock and so on, it's extremely important. Then, in order to improve sample efficiency, you can use meta learning, transfer learning, and off policy, and so on. Okay, so one other important aspect that has been, I think, widely used in also in the FINRL is that it doesn't necessarily needs to be only numerical data, but you can also use some sort of, for example, textual data. But textual data, in the end, it's absolutely very important, and so on. And I think I'm gonna just stop here. Right? The idea is I try to explore a bit, different formulations of MDPs and Markov games. Right. So I think, again, multi-agents is something that it's going to be extremely important, for example, for execution or for high frequency and so on, right? And also these policy methods with these new some sort of algorithms that allow to tweak, some sort to make more stable, like DAPO, like GRPO, that some sort of extensions or some sort of improvements to PPO and so on, and also this debate about distribution RL, which all traders need to consider, right? And I guess that if we see the amount of things that arise, right, you obviously interested into knowing the probability distribution of rewards of of a given policy, and incorporate or at least incorporate some of the information of the third moment, the fourth moment, and obviously what is things like causality and diversification and so on that are so important.
Okay, so thank you very much, Miquel. So maybe I suggest if we have questions in the audience, maybe it's time to ask it now. So that anyone has a question? Not yet. Because I have a lot of questions.
Reach out to us if today is not, reach out to us on LinkedIn if you want to have some sort of right. Again, we're gonna be publishing the paper and with more information in a few weeks probably, and then we have again the book with volume 2. We're going to talk about something I haven't mentioned here with these temporal differences with backpropagation to price American options, which is a tough problem, a really tough problem.
Yes, I have questions. Like you showed a lot of different strategies. Do you have like benchmarks to show the performance compared with let's say state of the art, like the previous state of the art? Because that's very important. At one point you mentioned one paper which was having a better Sharp ratio for the DGI. So do you have similar evaluations for other algorithms that you presented?
No, not today. At least not today. I also want to say something about that, which is something important, which is that we're all, let's say, finance is a little bit like LMMs, in the sense that it's very hard to build sodas or to build benchmarks that are actually useful, in the sense that, here I've defined many cases in which you're gonna need you might need a different RL model. I'm sure, right? You're gonna need a different model to use if you're trading Microsoft, if you're trading Apple, if you're trading